So let's talk about estimators for the fixed effects model now. I'll add some pages. Let's talk about estimators for the fixed effects model. For the fixed effects model. Yeah, so going back to the summary, so remember that we said that there are several options for estimators of the assumed models. So we already talked about the pool model, and now we're talking about the options that we have when the fixed effects model is the assumed model. As you can see here, actually, there are only two estimators that provide consistent estimates of the coefficient beta in the model, and those are the fixed effects model, which happens to be that's the preferred estimator, and also the first difference estimator. Now, I will only talk about the fixed effects estimator because that's the preferred estimator. We discussed the first difference estimator in the context of the pool model, and we said that actually it induces autocorrelation. So in most cases, what you will end up using is this fixed effects estimator. But if you want to derive it, since we already covered it for the context of the pool model, actually the derivation is very straightforward and very easy. But for the sake of time, we will only look at this, the fixed effects estimator for the fixed effects model. Okay, so let's going back. Remember, so we have our fixed effects model. Just to remind you the type of model that we're talking about. So remember that here the difference across the individuals are captured by this difference in the intercept. Just a summary of the characteristics of the model. So differences across the eyes are captured with difference in the intercept. Okay, and remember the other characteristics of this model. And this thing for me, there's something that I click once in a while and I don't know what's that. Are captured with the first in the intercept and also the unobservables. And here we refer to time invariant unobservables. In this model can be correlated with the explanatory variables included in the model. So as I mentioned, there are two consistent estimators. I'm going to emphasize this. So two consistent estimators for this fixed effects model. So one is going to be the fixed effects estimator. And I'm using FE for fixed effects. So for the model, so we can use the fixed effects estimator, and we could use the first differences estimator. Okay, so I'm only gonna be talking about the fixed effects estimator since that's kind of the preferred model. So Let's look at the within or fixed effects estimator for the fixed effects model. Once again, so let's start with the original model. So this is the original fixed effects model. I d prime beta plus AIT. The between transformation so for this model, so alpha I is constant, so it's going to be the same. So that's the between transformation, and then the within transformation is going to be the difference between 1 and 2, which we already learned when we're looking at the fixed effects estimator for the well, and here, since we already know that that's the same, so I'm gonna ignore that term, save some time. We know that that vanishes, that intercept. So this is the second equation, this is the third equation. T minus AI. Okay. And the fixed effects estimator is OLS on the within transformation. Is OLS estimator on the within transformation. So this is the fixed effects estimator for the fixed effects model. Okay, so very straightforward. So basically the same thing. As you can see, we start with a pool model with a fixed effects estimator. The within transformation, we end up with the same model basically. Now, so remember that here, if we apply this fixed effects estimator, those alphas cannot be estimated. Okay, so as part of the OLS procedure, but they can be recovered. So the alpha i's. So if that's interest, if you are interested in that, so the alpha i's can be recovered using this procedure. So I'm going to be using EI. Well, I think I should use alpha I hat. So alpha I hat is going to be equal to yi, so minus xi bar prime and times, and I'm going to be calling it BLS, the estimate for beta. Okay. Now, what about the inference for those intercepts? If we are interested, we can also use a robust variance covariance matrix. Then we can use the robust variance covariance matrix for the variance of BLS. Okay, it could be the robust or the general one. Actually, it doesn't matter. So for the variance of that alpha I hat is going to be equal to square t plus xi prime, and then here we have that variance. That could be, estimated using OLS, or we could use a heteroscedastic consistent covariance matrix. Okay, and what is this square? It's gonna be an estimate of the variance of the error terms for all of the observations. Prime BLS minus alpha I square divided by NT minus K minus N. So one way to think about this thing here, so basically what we're doing here is that we're calculating it, it's an estimate of the variance of the errors. So these are the sum of the square errors for all of the individuals across all time periods. I mean, it kind of looks complicated, but basically that's what it is. Okay, so remember the idea here is we use the fixed estimator, but we cannot recover those alpha i's because they vanish once we do the transformation. But if we are interested, we can calculate those intercepts using these equations. Okay, now how often we're interested in those intercepts? Not very often, but it's possible. Okay, once in a while you might be interested in estimating those intercepts. Now some comments here about this effects estimator. The first one is that instead of using this fixed effects estimator to estimate the fixed effects model, we could also use, it's also possible to use OLS with dummies to estimate the model. So if we do that, actually we'll be estimating both the alpha i's and also beta. Okay, and this procedure is called dummy variables least square estimator. So we could use that one. Actually, it's equivalent to the fixed effects estimator. Dummy variables least square estimator. Sometimes you're going to see LSDV. So it's possible that we use that one, and this is equivalent. So to the fixed effects estimator. Yeah, basically, Now the disadvantage of using this dummy variables estimator is, if you have like if you have a model with thousands of individuals, let's say 10,000 individuals, you are requiring the model to estimate 999,000 intercepts, which, in some cases it might cause some complications. It's feasible, but, it might create some problems. So if they are equivalent, especially if you remember, like when you are doing panel data models, most of the time the main interest is that beta coefficient related to the time variant explanatory variables. But you should be aware of that, and that sometimes that estimator is mentioned in the literature. So the second thing is, and I know that so far, when we pretty much have ignored the potential for having some time invariant explanatory variables that are observable. So remember, in the context of the fixed effects model, we can think as having two components that get into that intercept. So one is going to be a vector of observables, of observed time invariant variables. Okay, so of course, we know that in the context of the fixed effects model, we cannot estimate that. I mean, that alpha I is going to vanish. But in some cases, it might be possible to recover those coefficients, but they require very, very strong assumptions. If you are interested in that, actually our green textbook has a section where they talk about this thing. And again, and I know that this is I'm coming kind of out of the blue, because the main emphasis here in what we've been talking about is in the estimation of that beta. And we pretty much, we've been ignoring the potential for having some observable time invariant variables. But basically in the context of the fixed effects estimator, that's it's feasible to estimate these coefficients, but I mean you need some very, very strong assumptions, and most of the time that's not done. And I also mentioned this thing because during the lab, when we use like a pool effects model and also like a random effects model, we'll be estimating the coefficients related to some time invariant variables. Okay, but for the fixed effects model, that definitely is not even feasible to do. So I'm going to write that note here. Some cases we might be interested in the effects of some observable ZIs, which are called ZOI because these are observed on YIT. Okay, and the fixed effects estimator, remember, does not allow us to do that, but those coefficients can be recovered under strong assumptions. So the fixed effects estimator does not allow us to estimate those effects. But they can be recovered let me see, I'm going too fast. They can be recovered. Oh, again. Under a very strong set of assumptions. Okay, so if you are interested, actually, like in green textbook of econometrics, the latest edition is 2018. He talks about that potential, and that's basically what I wanted to talk about, the estimation of this for the fixed effects model. I mean, I only discussed the fixed effects estimator because that's the more popular one. Basically, we apply the within FX transformation. We use OLS. If we're interested, we can recover those coefficients. Another option would be to use a model with dummy variables for all the coefficients, but that can create some complications. And also in some cases, we might want to include in our panel data model the effects of some observed time invariant variables, but I mean, those coefficients are not estimated within the context of the fixed effect estimator. If you are interested, you might be able to recover, but that requires very strong assumption.